everybody. We're going to start off here with some 320, but if you're in the chat, say hi. We'll throw out some points. Let's go here. 123 BAS 320. Making models. Let's do it. Here we go. E-bots over there chatting away. So this is kind of some of the cool stuff we do in 320. So if you're in 320, you're probably watching this. If you're in 201, hey, check it out. I'm going to move my camera over here a little bit more. Perfect. So with this, we have right here lasso regression using tidy models from Tidy Tuesdays from Julia Seigel. Mispronounce her name every time. Silgi. I've got to go listen to her say her name again. Anyways, thank you very much. She's excellent with R, and she works at our studio, now known as Posit. But really great stuff right here. So check out her blog. We'll put it in the chat right here. And really great stuff right there. And so with this, she has a full video going over this, but I just want to talk about some of the kind of model building. You see side-by-side box plots right here. She went through and did seasons of The Office and looked at the ratings of them. So this is lasso regression, and we're predicting the rating. So let's just first look at this right here. She's just straight getting the data right here. So really amazing. Remove regex. She's removing out some things right there. And you can look, we can run her code, which is really cool. So I love when people post code. And so let's go here, load tidyverse, which is all the tidy functions. Then we're going to download the ratings. We looks to have downloaded them, removing certain things. And let's take a look. And here are the ratings for The Office. Wow, look at that. There's the pilot. It's pretty neat. So it's only showing part of it because it is a Tibble and Office ratings right there. There you go. Look at that. All the episode names, lots of episodes of The Office. Tons and tons of stuff right there. Come on, drink over here. Wee. And so this is The Office, all the ratings. And there's more variables, it looks like. We'll probably get into that right here. So here we go. There's the air date, the total views, the IMDb ratings, the title, the episodes, the seasons. So we got a bunch of information. All of it was just gotten from the internet in seconds, which I find to be amazing. So here we go. We're going, I haven't used this before. That looks like a package. Let's find out what happens when we run it. Does it run? And it looks like it's going to have more who wrote it and all this stuff. There might be is there an R package for The Office? That'd be amazing if so. I don't know if I have this package going right there. So let's see if it runs. There is no package called that. So we have to go over here and go install.packages and grab this. And that's an interesting package if it looks to grab additional information about TV shows or something. And it runs, and now we get the Office info, and you can see things. Who were the writers? Ricky Gervais. I should have known that. The director, the pilot, certain characters, I guess if they're in the episode. But we could take a look at the full data set right here. Office info. 55,130 observations with 6 variables. Whoa. There is tons of information right here. So tons and tons and tons of info to be gotten. And I do wonder what this package is and what it has in it. So what you can do is you can take the package and run this. Looks to be just for The Office or something. Let's run the question mark on it. And the entire transcript from The Office in tidy format. Well, I'll be. So that's what this package does right here. That's the point of it. And yeah, so we now have the entire transcript for The Office. That's the information we have. We're going to look at several different kinds of features for modeling. First, let's try to find out how many times characters speak per episode. Oh, it's the entire transcript. What? So she's figuring out how many times a character speaks per episode. Hey, Jesse, good to see you here. We're kind of looking over some code real quick and what's possible. We literally have the entire transcript for The Office right now for every single episode. So I think we're missing the one row right here. If we go to this Office info thing right here, I wish it said what they said, but we should be able to see that. So here is, we're taking character info, count the times the character. Oh, so it's just filter character count greater than 800, which doesn't seem like we would have that. And so now we go right here, episode name not found. Dun, dun, dun. Her code should work. Uh-oh. So we run into a little boop right there. Did I not run all the code? Here's the code as is. Take all this code right here, which that's everything. I know, right? So there's all that code. We got all that code. Then we go down here and we grab all this code. And our code should run in order. It says episode name not found. Let's go see where episode name is used. Ooh, they might have updated. Wait, string remove all, episode name. String to lower, episode name. That's just gonna make everything lowercase. String remove all. String trim episode name. Let me just remove this. Still doesn't like it. They might have changed the package, which is the problem. They might have removed out the ability. And let me look at her code. Because it's not showing in episode. There's episode name right there, pilot. So we should have that too. There's episode name. Episode underscore name. And it says object episode name not found. And feel free to ask any questions you have. There it is. There's episode name. That's got this. Here, let's run it bit by bit. See where it breaks. That has episode name. That should work. That's episode name right there. Episode name not found. Let's do this. Let's just run it with character. I think I know what it is. I have an idea. I think I know the issue. If you're wrong. I think the function could be from another package. And I'm worried. Let me do this. I think I know the issue. I think the issue is, so let me X out of this. Don't save. Because whenever you hit something this weird, sometimes it's best just to restart R. I think I have something running that is kind of overlapping with the function. And if everything looks like it should work, then you might just have a problem where you've loaded something that is causing issues. And the answer is, it runs now. Yep. So that is probably one of the hardest errors to fix, because I think I had something running that was causing issues where it wasn't running properly. Count is a dplyr function. If you look back, it said plyr a second ago. So plyr and dplyr are different packages. So the way the function was working was different than it was meant to. So although this said count, which is correct, it was a count from another thing. So there's like two different libraries, one that has a count function, another has a count function, and I was using the wrong count function. So I was like, if something doesn't work that much, at some point you're like, I probably just need to reset R and rerun this. But that's a very, I've had students spend hours being like, it just won't work. I know, right? So now what's so cool is we literally have right here a count of how many times characters speak per episode. So here's the episode names, and here's how many times. Man, look at this. Angry Y, who's that? Oh, that's the name of the episode, Angry Y. Back from vacation, you can see who speaks, like Andy. You could even sort this table right here, which is really cool. If you go to characters, if you want to see a Dwight episode, your best Dwight episodes are going to be AARM, our junior salesman. If you want to see like a Jim episode, you can see which episodes. There's only one episode where Jim doesn't speak at all. That's interesting, right? And the main character in that episode is going to be Michael. Dwight, there's not a lot of speaking in that episode. If someone knows that episode, Banker, then pretty interesting. But you could go through here and see which episodes are more heavy on a certain character speaking. And this is the power of coding, how we were able to get this so quickly. It might take me a little longer to write the code, but you could go through here and figure out which episodes. Look, Kelly doesn't have any. The amount of times Kelly speaks is never more than 30 times. Interesting. Just that's I was shocked that it's Pam right here. Where's how many times Pam speak? 126. Woo! Over 100 is a lot for any character, it looks like. Michael has a lot. I think he's one of the main characters, right? I never even watched The Office. Phyllis must be a side character. Ryan. Toby, side character, it looks like. Aaron. Jan has... And then it's interesting, like, just to see... Over 100 is a lot for anyone. Even Dwight hasn't spoken over 100 times. So Jim, big character, if I had to guess. Jim, Michael, Pam, Jim, Michael, and Pam are probably the top ones. And so someone who knows The Office will be like, oh yeah, Jim, Michael, and Pam. Those are your big three right there in The Office. So pretty interesting. We could look at the distribution actually of all of these. Could make stacked histograms of each one, or like you think about how to display this data right here. You could just make a histogram of observations to talk about this and look at the values. So that's what we've been doing in 201 a lot. So that's interesting, the table we get talking about how much character speaks in an episode. Next, let's find out which directors and writers are involved in each episode. I'm choosing here to combine this into one category in modeling for a simpler model. Okay. So this is basically who wrote the episode and who directed, I think, too. So the creators of the episode. And there you go. Pretty awesome right here. So we've got all the different people. So this is a binary operator, whether or not the person worked on the episode. So we got the creators right here, and you can just see all the people who worked on The Office. We could look at the count of observations. Everyone from Gene Stupinski, Lee Eisenberg. Oh, I think I've heard Lee Eisenberg. Like, they've done a lot of stuff. But yeah, pretty cool right there. So there's the creators. Next, we go right here. Next, let's find the season's episode number for each episode. And then finally, let's put it all together into one data set for modeling. Okay. So now we're just getting the seasons. The code is amazing. Like if you go through each step of this and be like, okay, what's going on? Here we go. So there we go. We're kind of putting everything together into one. We're doing joins on the episodes and the characters and the ratings to get it all into one data set called The Office right here. Well, that can't be the full thing, right? Oh, yeah. We're bringing it together so you can see the episode name and then how often a character speaks on the episode and who worked on the episode and the IMDb rating. I mean, imagine so think about how this is valuable. You work on a TV show and you're trying to figure out what people like. So now you know who writes the episode, who directs the episode, how often characters are in the episode, what episode number it is, what season number it is. So all of a sudden now you can look at it. We can even do a time plot of this to see what was the trend in Office ratings. I could probably get that pretty quickly, a time plot on this. You know what? Let's try to do that. Let's take a little bit different of a path right here. But this is like a fun, hopefully you'll watch this. I don't know. But if you have questions, let me know in the chat. I'm going to load up library FPP3, one of my favorite libraries for this, to get a time plot going of this. Hopefully it doesn't cause issues. And we are going to we need to turn it into as.tisble. And with the as.tisble, we are going to go and take The Office. Hey, Brandon, good to see you here. Feel free to ask questions if you have them. Index equals episode. It's mad about that. We could do it as like a week or a day. It's going to work as a time plot, but time plots are over time, and trying to think how to, and let me go to the FPP3 site. So let's bring up the FPP3 book. I think that'll bring us to it. Mubot, help us out. Bring us the FPP3 book. Mubot. Is it !FPP3? Need to put both those commands in there. Very rarely do people type FPP3. And Mubot should be put in the chat. Mubot, you awake, man? He's not listening to me. Or is it FPP? Should see that. He's not listening to me today. Last try on it. Then I'm going to go look at it myself. There it is. Gosh. It's !FPP. Just FPP. Okay. Here we go. Now we go over here and we take a look at getting started. Tom Series graphics. Tisble objects. He's put in videos for everything now. And here we go. Let's turn it into a Tisble. Here we go. Oh, geez. They do it this way now, which I'm not the biggest fan of. So they updated their way of doing it. And they used the new pipes. Mutate month, year into month. Okay, we want to take object office. Pass it through right here into the mutate. I don't think we need that. As.tisble index equals episode. But it's mad about that. Yeah, we could try to... We'll take this out for the moment. Doesn't like it. Tisble must have distinct row... Oh, it's like... Oh, I think I know what's going on. it restarts the episode number. Okay, so let's go here and go to, it has 136. Let's go to Office, episode number 1 through N rows, Office. There we go. Okay, that's got that. And now let's go episode number, delete, run. Got it. Okay, so we're going to go and store this as Office Tisbel object, time series, auto plot, or we go Office, time series, auto plot, and it's rating, right? Oh, no, I thought it'd be that easy. Oh, no, it's like IMDb rating or something. IMDb underscore rating. Will it show up? Damn. IMDb underscore rating not found. Okay. Well, then Office, time series, IMDb underscore rating. There it is. Whoa. Pretty interesting. So, throw some models on this really quickly. But The Office really, man, it was going down at the end. It had a big spurt up at the end. But that final season or so really had some changes going on, right? Or there was a peak around episode 50. Kind of see a little bit of a bend throughout the model there. And so what we could try to do, and this is what I love about, using different models right here. I mentioned this in the second class, I think, about time series models. And so what we'd want to do, let's run an ARIMA on it. Here's ARIMA, good. We don't really have seasonality of it. So let's go ahead and run an ARIMA. See what's going on right here. And there we go. Let's try to make, there we go, forecast, filter, autoplot. Let's get a fit for it. Okay, so let's get a fit. Yeah, he's updated all of his code. Here we go. He's piping that through. We don't need to do that. Okay. So here we go. We're going to take the Office time series. Oh, no, he's taking the fit. Run your model through here. We're not going to filter. We could do certain seasons, but there we go. That should do it. We don't want to call it cat fit. We want to do IMDb rating. Oh, and then he's doing a stepwise a search at the end. Well, you really only have to do the search. So that should do it. And let's call it Office fits. And that should run it. Export's not found because they didn't change the last one for the Y variable of interest. Parks and Rec is better. Cool. Yeah, it's got what's his name in it? Chris Pratt, right? Oh, he's in both, isn't he? Is Chris Pratt? No, he's only in the one. So here's the fits for our models, and we should be able to go here and look at this. Can we do glance on it or something? I'm trying to remember the codes to. There we go. It is glance. The AIC for the search is the best. There's the stepwise method right here. So it looks like the search method in the AIC is better. Good stuff. Okay, cool. And now we go right here. We could take a look at the model, look at the residuals from the model, see if they're normally distributed, see if there's any unfound lag problems. Augment, don't gotta worry about that. P-values are good. High P-values are good for this. And now let's take a look at actually plotting it and see where the model was heading. So here we go. We're going to take our Office fits. If the Office had continued on, and we're going to take the search model and plot IMDb rating. So if the Office had continued, IMDb rating not found. Why is it not found IMDb rating? Do we have to update the fits? Piping it through. It should do it. I did not like that. What does it find when we do this? Okay, that's good. Why did it say it didn't find IMDb rating? Okay, let's just do autoplot on it. So that is the trend that we would think the Office would go afterwards. So that's just the prediction. But it should be auto plotting. And I've seen this happen when he does it in the book. I've seen where his code doesn't work perfectly when we do it. That's where he's plotting the rest of the series on it. And this is the prediction. And we want to put that onto our original series. And what if we go here? Oh, I think I know what I got to do. It's Office Time Series. There we go. So we actually predicted would go back down. To look at a smoothing model throughout this, let me actually do a decomp of it. So it's pretty fun just to look at data and see what's going on, what happened through it. Here's time series decomp. Let me run a decomp on it. Sometimes I even have to review the codes to do it. So here we go with the time series decomp, looking at the trends in the data. Yeah, I do too. It's just fun. So what we're going to do is we're going to get sort of this pattern throughout here. We're going to see what's going on with the, so let's take the trend in the data from the office. So all we're doing is just looking at office ratings right here over time. We're just going a separate way using some techniques right here. So we first have to create the decomp. This is the decomposition object. So what a decomp is think of something like waves of sound, and then you're pulling out like different waves. Now that's actually like Fourier method right there. Fourier is pretty interesting because Fourier, I think it's called Fourier. That's what it is, Fourier. Someone told me how to pronounce it. We need to create the decomp object first to decompose it. So let's first create the decomp object, which my brain's blanking on how to create the decomp object. It's so cool. You can just like see what's going on as you adjust parameters. Where is the decomp object created? Create the decomp object. Here it is. There's where he creates the decomp. Okay. So this decomposes it into different trends like over time right here. We're probably only going to get very little. We don't have a seasonal component to this. So we're going to take the Office time series data, stored into the decomp object. This is seasonal. Yeah, can we do the STL? Because that is seasonal trend linear. We don't really have a seasonal. Well, if it gets mad at us, it gets mad. That's the way it goes. We'll just run it and see what it does. And does it work? It works. There we go. There's the decomp components. And now we can do this. Title is Office Ratings. And it got mad, employed not found. IMDb rating, change that. And there you go. Man, look at that dip at the end of it. And we could change some colors here. But yeah, The Office did kind of hit a peak around episode 48 or so. And so you can see there was a huge dip towards the final episodes, but this is kind of a smoothing trend across the data. Yeah, so it's pretty cool how we can, talk about what we see and the general trend in the data. The Office was gaining a lot of steam and then started to lose it. And you just kind of see this. What we can do is actually call it a piecewise regression on this, because especially here to here, it's kind of linear up, here to here. So piecewise, there's what's called piecewise linear regression. And what you try to do is, instead of using one line to describe the data, use multiple lines. What was the global minimum? Oh yeah, I like that question. The global minimum is down here, closer to like maybe 7.8, and that would be like an average, because remember the lines are estimates. So piecewise regression. Good to see you, Didi. Good to see you, Jesse, and anyone else in the chat. So we might have a piecewise regression with 1, 2, oh my gosh, 2, 3, 4, and 5. Does that make sense what piecewise regression is? We don't cover it in 201. We cover it in 474. You do one piece right here, one piece right here, one piece, one piece. There's algorithms we have to do this where we try to optimize it. But yeah, so that's called piecewise linear regression. There's also, I think they're using they're not doing local regression here. There's just so many different ways to do regression, and you could just fit multiple lines instead of one line. But then the question becomes how many lines. So you tune like you tune a radio to figure out how many lines to fit, because you could fit like 1,000 lines. Yeah. So what this is a, what is it? Season trend linear right here. So this is what is called a decomp. So decomp is super cool. We're just doing some advanced kind of stuff right here. So you notice how this is total employment in U.S. retail. When do you think there's this spike in employment? Speaking of 474, about to start my final project, and I haven't looked. Yeah, just start it up, Brandon. What do you think this spike right is here in U.S. employment? Take a look that it's a little bit before January. If that's where January is, you're seeing a spike in U.S. employment every year. When do you think that spike in U.S. employment is? Like, just kind of thinking through it, why there would be a spike. And that would be right there, the seasonal spike. So you've got kind of a cyclical pattern. You've got the cycle that is irregular around Christmas, exactly. So there's a seasonal pattern. There's a linear pattern. Like, if you think about the linearity of this, if there was some sort of linear pattern right here, it might have a sort of like upward linear trend, but then there's a seasonal pattern, and then there's like an irregular pattern going throughout it. So what decomp does is it breaks these down. So here's the decomposition of it. So here's the trend cycle. I think this is often called trend cycle right here. You can see it's kind of it's got a little bit of a cycle. Cycle's irregular. So this right here is the trend, and this is the seasonal pattern, which is actually getting weaker. Trying to think, I think this is a multiplicative decomp. Good to see you here, Jack. So you can see the spikes, but there's also a decrease. And then this is the remainder right here, which is literally the residual. This is the unexplained portion. So what's interesting is when I ask people, which of these is the biggest component, this is going to be a trick question. Do you think it's the first, the second, the third, or the fourth is the biggest component of this time series right here? And then we'll look at ours. Do you think the first, the second, the third, or the fourth is the biggest component? Now, the first is the series. That's the actual series of data you're looking at. Like, that's your data. So first really doesn't count. But if you realize that the first is the total variation, then the biggest component here is the second. And you'd say, well, wait a minute, this looks pretty big right here. These right here are scale objects. Like, each one of these is the same size. Like, this is the same size as this, is the same size as this. So you'd have to really zoom in to see the remainder. Also look at the scale on the remainder. It goes from 100 to negative 100, where the scale on the trend cycle goes from 16,000 to 13,000. Yeah. Oh, no, yeah, exactly. And so it's pretty cool to like look at this and see like what makes up your series, that there's a seasonal pattern that is a good portion of it. Then there's the trend cycle, which is the biggest component of it. So that sort of increase, kind of a little bit of a flow, is the biggest component. So we should be able to run this on our data, the office data right here. We're just going to auto plot our time series. There we go. Ooh. Why am I not happy? Ooh. What is the biggest component of our series right here? That is not good. The biggest component of our series is the what? The biggest component of our series is the what? And there's that trend cycle we just saw. The biggest component of our series is the remainder, because this is a little bit smaller. I know it's counterintuitive to think the smaller thing is the bigger thing, but remember, these are all the same size, so this is like a larger scale right here. You can kind of see 9.5 to 8 and 1 to negative 1.5 is a distance of 2.5. This is a larger scale right here, and this is a 1.5 scale, or 2-ish if you count down to there. So why is it bad that the remainder is the largest portion? What is the... Because... Well, the thing is, the remainder is kind of the irregular ups and downs we're seeing, and the remainder is the best explanatory. So you know what that means? It means that we really haven't done a good job explaining it. So if what explains it is the unexplained portion, does this make sense? The remainder is what we haven't explained. Here's the trend, which can partly explain the data. And if you look how this dips down right here a little bit, you notice how this doesn't dip as much. See how this doesn't dip as much as this dips? That's the trend, and the trend has been removed. We've decomposed it. This series, if you put these two things together, you will get this right here. Does that make sense? See this little up pattern right here? It doesn't really go up right there. That bump up right there is a lot less here. And you see that big swing up at the end, this big swing up? Well, that's been removed. It's been decomposed. So decomposition takes a series and like decomposes it into parts. And now the best explanatory power is the remainder, which is the unexplained portion. And you don't want the remainder to be the best thing, because the remainder is what you haven't explained. If you look back at the book where they have a much better version of this, or one that works better, if you notice the remainder looks kind of what? 6-letter word. Let's throw out some 10,000 points. Didi, do you know the word? And Jesse, do you know it? The remainder here should look kind of what? And it does. The remainder actually looks pretty good because it doesn't look like the original series. It looks what? 6-letter word, starts with an R. I'll give you a hint. The remainder should definitely look random. Yep. And so DD pointed out exactly that it doesn't look random. It looks like the original series. And so with that, we actually have a problem with this. And these are the things that we try to learn and still hold true if you get to the upper level classes, that you want your residuals to be random. You don't want them to have a pattern in them. So we talk about that in chapter 7 and 8 on test 2, I believe. So everything you're learning right now, Jesse, if you choose to go on with statistics, will continue to be important right here. So it's really cool. That's what I love about stats. But what? So it looks like it doesn't do a good job. We kind of took a different pathway on analyzing this data. And Himly Post, if you didn't see DD earlier, this is what we were doing right here. So actually everything right there can be ran. To be honest, the IMDb rating, I guess it is. And she does a really good job on this. So here is what did she do right here? Encourage you to check out this screenshot of Michael Arthur Dave, who's similar. Gregson was EDA on Twitter. So this is the episode, but IMDb rating, but of different individuals? I don't know what that is. Train a model. This is where she creates her models. And when she creates her models, here's what's really cool at the end of this. And Jack, if you have any questions, let me know. So a big conceptual thing, Jesse, where do you think, and DD answer to if you want, where do you think the models are better? Over here on the right side or over here on the left side? Now, in 201, we only teach you R squared. So is it better here, here, or here? Where do we have the better models? Where do we have the better models? Now, we only teach you in 201 R squared. Would it be better here, here, or here? Think about R squared. Hey, Jason, good to see you here. So think about what R squared means. R squared is the percent of variation Y explained by the variation in X. And she really doesn't get that good of an R squared, which is kind of what we were going towards too. The R squared right here is about 13%, 13, 14%. 13% of the variation in IMDb rating is explained by her model. It's not a lot of variation. Towards the right, and it'd be better right over here because you want R squared to be as high as possible. Great job, Didi, right there. You want R squared to be as high as possible. And a key letter to RMSE, when you see RMSE, it stands for root mean squared error. So think about this. What would you like your error to be if it's root mean squared error? So you'd like your error to be what? Very what? If it's root mean squared error. So just realize we can calculate what is the root, the mean of the square of the error. Well, the errors are the residuals. So we square them to make them all positive. We take the mean to get the average, and then we root it to bring back to the units of the problem. So that's why we do root mean squared error, mean error, lower. Yep. And so what's neat, if you ever hear terms like MAE, so think about MAE right here. MAE stands for mean absolute error. So once again, these error things right here, you want to be as small as possible. If you ever hear MAE, you want it to be smaller because it's error. If you hear MAPE, that's mean absolute but percentage error, so you want that to be small. Then there's SE, mean absolute scaled error. It's just a bunch of statisticians came up with a billion ways to do this. I think there's mean absolute scaled percent error, scaled. So it's scaled, so it's kind of all the same. There we go. But all those things have error in the term. You want them to be smaller. So whenever you see MAPE, MAE, RMSE, you just want them all to be smaller. Smaller is better because it's error. And that coincides with our idea that R squared higher is better. But here's the big thing here for 1,000 points. These look to be kind of what's-is. Now, if you look, they're based on standard errors. And you're actually seeing we go to the mean plus one standard error. I will throw 10,000 points if anyone can tell me what that is and exactly what percentage it is or close to what percentage it is. So think about it. It's the mean plus or minus one standard error. And you might say, have we done any 201? This is 201 right here because we're going to the mean and we're going plus or minus one standard error. That's what we're doing. Well, not kind of like a z-score, but what does this look like? That is what they wrote out. They said go to the mean and go plus or minus 1 standard error. Not 51%. I think Jesse and Didi are on the right track, but think... I know what I'm talking about. Because... And so they're building what are they building? I mean, I'm writing it out. What are they building with this equation? What are they building? And then you can see it there visually. Did 68 what? Those are 68% whatses. You're 100% right. Let me throw those 10,000 points. Jesse, you're going to... Didi, you probably got lots of points too. Check out your points anytime. I've got the most points. Jesse's in second place though. Just because I'm here all the time. If there's ever points, I'm here in the chat. I've got 12 million points, I think. So they are building 68% confidence intervals. And take a look right here. We have good reason to believe that the typical miss the model makes is a lot lower right here. But does it explain more variation? The variation differences between the models is not statistically significant, but it does have a much lower error. And then we could make 95% confidence intervals if we just change the standard error to basically 2 standard errors, or 1.96 close to. Probably 2 if you're using T's. You can just estimate about 2. And good to see you, Alexandria. Does that make sense? Like, you can see there's a big difference between here and here in the RMSE, but oddly enough, the R-squareds kind of overlap. The fact that this interval right here overlaps with these other ones, there might not be that much of a difference. You hit 1 million. Nice. I love it. I love it. That's awesome. It was so cool seeing people hit the points yesterday. And what's really neat here at the end of this is we get and it's weird, there's a non-linear trend to episode. But if you think about look at this. Good to see you. Can you please do that? Let's do Paul Investigates next. Yep, let's do it. Take a look at this. It looks like people didn't... Did anyone... Let me finish with this. Did anyone watch The Office? Did anyone... If you are in the chat right now, and then we'll do Yoda's question right there. Did anyone watch The Office a lot? Did anyone watch The Office a lot? Like, does anyone like... I'm a huge Office fan. Seen them all. Love The Office. I was the worst error in The Office earlier, not the global minimum. Oh. Were they the worst error in The Office? Ooh, yeah, I wonder. I don't know. Good question. I'd have to find out. But if you watched The Office, the most important thing for figuring out The Office, like the rating, would be the episode number. But the most important characters would be... Oh, Greg Daniels is a writer. That's why it's Greg_Daniels. So episodes written by Greg Daniels were rated higher. Like everything else, the same. Episodes by Greg Daniels. But people really like it if Michael is a character in it. Oh, yeah. It is. I love Philip DeFranco. So, or his show. Been a fan of him since 2012. Yeah, 2012. Watching as someone got me into Philip DeFranco in 2012. I remember. So, been watching. Oh my gosh, I've been watching Philip DeFranco for 11 years. 11 years of Philip DeFranco. 11 years, 1 month, Philip DeFranco. So Greg Daniels as a writer, very like his episodes get higher ratings. If you look down here, but these are less important. The real importance in the model is going to be, did Greg Daniels, or the real importance in predicting the episode is how far are we into the season? That's going to generally have higher ratings. We did see a bit of a nonlinear trend. Greg Daniels writing it is going to be something that's going to lead towards higher ratings, we would think, all other things being the same. And Michael, Jim in the episode are going to be good right there. So pretty interesting to look at this and think about if you are somebody, like if Greg Daniels asks for a raise, what might you do? Would you replace him or maybe give him the raise? What would you make as a business decision seeing this? If Greg Daniels comes to you and says, I need you to give me 5% more money. I need a 5% increase from last year. Are you going to say, we're going to look into other... Yeah, you might say, his episodes are getting the higher ratings. All other things being the same, like... Because someone might say, well, maybe he just got to do the episodes with Michael in it or Jim in it. Everything else equal. That's what regression accounts for, is everything else the same. Greg Daniels accounts for a higher IMDb rating. So that's pretty interesting right there. Season. Ooh, you see later in, so the earlier episodes in the later episodes in a season, the further you're into the season, the higher the ratings. But the later the season, the lower the ratings. Season, everything else the same, has a negative coefficient. So season is negatively correlated with rating, but episode number is positively correlated. And we can see this right here. So this is a really cool, hey, Colin, good to see you here. Pixie Dust from Disney, we love it. So really cool stuff. And Kevin, apparently, Lee Eisenberg just doesn't impact episodes. Like that Lee Eisenberg, just no impact. Is it interesting or something else you want to cover the grass for Superman, Lois? Oh yeah, well I don't know. Is there? Can you show me? So this data right here, that'd be really cool. So that's the new TV show, right? I don't know if I have that data. Do we have that? See if you can get it for me, Didi, or a place to go. This is a blog that kind of got us the data. But if we could get that, if you can show me how to get the IMDb ratings, or we can look into that, we'll do that. Let's do, is it the political one? And then we could come back and try to do that. I love having some fun with it, because that's the real, application of statistics, is asking the questions you want to look at it to say, like, especially if you're a company or a broadcast company trying to think about renewing a show for another season, well, this is the questions you ask, like, what will be the ratings next season? Will it have good ratings? Well, let's make a predictive model. Okay, we just lost this writer. How about we get this writer from another TV show? Do people generally like what this writer does? So you could look at this, like what we just looked at right there. You could say, where is it? Should we be hiring this writer? And that's where really statistical decisions are going to be the best ones, because it's like, okay, this writer was generally a positive force on this show, that their episodes were rated higher than other people's episodes. So yeah, you should try to make statistically sound decisions based on data. So we'll try to do I'd like to look at some Lois and Superman and Lois. Show looks pretty good. I haven't seen it much, but I've seen some clips from it just because I'm a comic book nerd. And let's see right here. The question was, poll investigates respondents' political affiliation. Here we go. Poll investigates. Here we go. Let's put it in the notes. In fall to three. A poll, stat 201, and chapter 19 quiz. I don't remember what chapter 18 is. A poll investigates. Investigated. Yeah, let's try to do that here next, because we only got one question on the roll to do today. So here we go, Jacqueline. Yeah, ask a question, Jacqueline, anytime. With this right here, when we do the chi-squared test of independence, how do we write the null hypothesis? Who remembers how you take this data right here and write the null hypothesis? So this is a key. Whenever you're doing the chi-squared test of independence, you will have two categorical variables, like region someone is in. So this is their region. And then this, oh, that's not their region, that's their party. Within a week, they're supposed to have it rated by Friday. So this is party, and this is region. So how do we, no worries, thank you for asking. How do we do the chi-squared test of independence when we look at party and region? So don't look at their answers yet. Try to walk through and be like, okay, I'm doing the chi-squared test of independence. So all we do is put between the words independent. And then the alternative will be not independent. Now, it's important to know that independent means they're not associated. So when you're saying two things are independent, you're saying that somebody's party or somebody's region in the US would not influence what party they're in. So try to think about it not just as memorizing the words. That's kind of the first step. Memorize what we do. Chi-square test of independence, we just put independent between the two. But then think about what independent means to say if someone's in the West or the North or the South. It doesn't matter. Their party is not going to be determined by that. That's the null hypothesis, is that knowing someone's region would tell you nothing about their party. So I'm going beyond just saying they're independent. I'm explaining what it means to be independent. That one bit of information, the value X, someone's region, would not help you understand the party they're in. So the null is independent, that political party is independent of region, and the alternative is that they are not independent. But do understand what that means. Now the question jumps straight into find the chi-squared test statistic. Now, we did a longer version of this yesterday. I want to point it out where you should be able to find all of this by hand. So you should be able to do every step by hand. This is something we did yesterday right here. I'm just going to show it, but I'm not going to do every step right here because you would first see the observed counts. The observed are what you see in the table. These are all the observed counts. This is a 3x3 table because there are 3 regions and 3 parties. There are 9 cells inside of it. So yesterday we had a 2x4 table. And so you see right here the 2x4 table. Now you might say, but that's a little bit bigger. Don't count the totals. You should have the totals. Once you have the observed, like there's 280 or 129 females with early preterm under 20. So there's 129 right there. And now we go down here and you can see the expected calculated from the row total times the column total over the grand total. You calculate all the expecteds. And then from all of the expecteds, you calculate all the cell chi-squareds. From all the cell chi-squareds, you add it up to get the Pearson chi-squared test statistic. So check out yesterday's video, especially where we went into a big detail. We did all these steps right here to solve out each one of these, showing that it can be done. But the issue is this takes a while to do. So rather than taking a very long time to solve it by hand, we're going to use jump. So get ready right here. First, click the little box and copy to clipboard. Now go ahead and hit Control-C or Command-C. With Control-C or Command-C, it's in the copy of your computer. Now you want to go anywhere inside of Jump. You can be anywhere inside of Jump, and then go to File, New, Data Table, just anywhere inside. Click anywhere inside Jump, File, New, Data Table. Once you've gone to File, New, Data Table, you want to then, don't click inside of it yet, go here to Edit, Paste with Column Names. Very important that you paste with the column names right there. Now that you've pasted with column names, you'll see it all at the top right there. Now, this is not the way the data should be formatted yet. It's currently red, blue, blue, blue. If it's not those colors, make sure to paste with column names. Let's go over here and go to Tables and go to Stack. I almost said Tools. Tables, Stack. With Tables, Stack, you're going to click only the blue columns twice. Double click, double click, double click. So make sure it has only the blue columns right there. Don't put the red column in there. You're going to stack the blue columns. That was Tables, Stack, stack the blue columns. So now we're going to click OK. And now we have our data properly created. You can double click the columns if you want. This is optional, and call it region. That's fine right there. You can double click this one if you want and call it party. These are optional things. You must make sure though that this is red, red, and blue because the first 2 are categorical and then the last one is count, which is quantitative, but that's the count of the categories right there. So it's just telling you how many people were in the West and Democrat, West Republican, West Independent, and those are counts of the observations in each group. So with this now complete, we are going to go to Analyze Fit Y by X. Analyze Fit Y by X. We're going to put right here, does somebody's region explain why they are in a certain party? Just look at the circularity to that. We say, does somebody's region explain why they are in a certain party? Because the X is the explanatory, the Y is the response. Why is this? Why do people join a certain party? Maybe the region they're in explains it. But don't forget to put the data in the frequency. This is the count of the observations. Pause right here. Make sure your screen looks like this so you can get the right data. Now, with this, it's going to solve everything for us. Everything's going to be solved now. If you look, the West has more Democrats. And if you don't like how the colors are, because the way we talk, at least in America right here, is Republicans are red, Democrats are blue.
It doesn't matter.
But that's the way it is. You don't have to set the colors, but this is confusing to you. Right here, make that blue. Make that red. There we go. Might make more sense just looking at it visually if you just want to kind of analyze the data, where apparently in the West, there's more Democrats. In the North, there's more Republicans. I think they're randomizing the data because what we know about in America, North is more Democrat, South is more Republican. West might also be more Democrat. They're saying the South is more independent. I don't know if I don't know if this is real data. I like real data. But that's what we see right here. The North has 43% Republicans, where the South has, and it's a small sample size too. Yeah, so we can't say it causes it. Because there could be lurking variables. There could be other things. There could be bias in the research. So there's a lot of things to talk about. And great job, Dee, right there. There's so much to talk about because, and we wouldn't quite call this correlation. We would say association, since it's categorical variables. So we'd say association isn't evidence of a causation. So two categorical variables are said to be associated because we wouldn't say region is correlated with party because you can't say as party goes up, region goes up because correlation is like positive, negative. And the correlation coefficient R is found by looking at the correlation between two connected X and Y variables. So you'd have to make a scatter plot. But no, those are great questions. And it's commonly said that things like this have correlation, like someone's region is correlated with their party. But we could say someone's region might have an association with party, and association doesn't mean it causes it. The big answer is that the differences we see here, who wants to say it? All these differences up here that I'm seeing are what? And that's the answer. And then we'll show how to get the answers for the my Pearson. All the differences, because the null hypothesis was that region is independent of party. We are going to fail to reject the null hypothesis. So that means we do not have evidence that region is not independent of party or that there's an association. So we don't have evidence. All the differences we see right here, like this compared to this, compared to this, compared to this, all these differences, the p-value indicates to us are likely by random chance. So the high p-value right there. Now, if you were to work this all by hand, which you could do for fun or for practice, here, let's do this. You ready? Try to find. So this is a good review. If you are studying for the test right now, you should know how to do this. So you ready? We're going to just do a few of these. The first thing after the counts is to get the expecteds. How many Republicans from the North would you expect? 1,000 points. So try this. This is a good test problem right here. How many Republicans from the North would you expect there to be? So I'll give this a moment. How many Republicans from the North would you expect? We'll give it a moment. So how many Republicans from the North would you expect? What do you think? I'm going to have to reset the points before May term. It'd be really sad. But if you come back, I give you like 1,000,000 points, or I give you enough that you're at a crazy level. You keep your hours, though. So we have to do the formula, row total times column total over grand total. So we circle the numbers. There we go. So this is the equation right here. Row total is that. That's the row total. Column total is this. Grand total is this. Doesn't matter which way you multiply them.
It doesn't matter.
So if we take a look at this, the formula comes out to 69 times 78 divided by 206. So 26.12. And we don't need to solve this because Jump can do it for us. There's that 26.12. So now we want to find the cell chi-squareds. Now, once again, we're just showing that we could find all these values by hand. So I could have found all those cell chi-squareds by hand. I don't want to do it. I'll just find one to show we can do it. So now we have to find cell chi-squareds. The formula for cell chi-squareds, and think about this. What are we finding right here? So that's just the what between those numbers. So feel free, I'll throw 1,000 points for all these answers. Just think about the formula before I write the whole thing. That's just the what between these numbers. All that is the what between those numbers, just mathematically speaking. And the count is the observed, if you're wondering. That's the observed. All that is right there is just a what between two numbers. Like this formula would just find the what between two numbers. Find the difference, right? So the difference right there is what we're looking at. And then we square it, because if you square something, it's going to be positive. If you don't square it, summing up the cell chi-squareds, which is what we'll do later on, would come out to 0. So by squaring, you get the chi-squared. And what you're getting is basically a squared discrepancy. But I like to use this example is saying, what if you expect to be paid $10 and you're paid $110? Well, that would be a big difference right there. So you would look at this and be like, well, I got 100 or more than I expected. You square that and divide by 10. That's going to be a very big difference. But what if it's like your salary over a year and you expect to get, let's say, we expect to get 110. You expect to get $50,000. and you get $50,100. So would this be a big difference right here? So if you could you go over a certain yeah, we dealt with next year, Robert, you got it. So think about this. If you expect your company to pay you $50,000 and you get paid $50,100, is that a big difference? No, it's not really that much of a difference, because when you standardize by the expected, which is the bottom part of the equation, it doesn't turn out that large. So that's why we divide by the expected right here to kind of standardize the differences and give them some context. So with this right here, let's solve one of these. So Robert, what do you think? What is the cell chi-squared for this one? It looks to be about 0.6. If I had to guesstimate, I'm going to say it's about 0.6. What is the cell chi-squared for that one? So you have to do observed minus expected squared over expected. These are just like test questions right here to solve the cell chi-squared. You do get these formulas on the test. And so what is the cell chi-squared for that? So you have to do observed minus expected. Observed is count. So if you look, I'm looking at their difference. The difference is about 4. 4 squared is about 16. It's a little bit smaller, so it's like 15. 15 divided by 26 is like 0.6 or so, I think. Yeah, it's about 0.6. So let's go ahead and solve this out. Remember, try to solve these to see if you can do them, because we do put questions on the test just like this. There we go. And so when we solve this, here we go. Let me disappear. Oh, great job. I said about 0.6. Thank you, Robert, right there. Great job. We'll show you some points here in a second. And this is really good practice to know if you can do it for the test and just memorizing how to do it. And there it is right there. And here's the thing, though. All those values that we're finding, Jump can find them for us. 0.574. So what would you then do with all these cell chi-squareds right here? So now that you have the cell chi-squareds, what would you do with all the cell chi-squareds? What would you do with all the cell chi-squareds? What would you do with all the cell chi-squareds? If you take them all and sum them up, you will get the Pearson chi-squared test statistic. So we take all the cell chi-squareds, all those numbers I've highlighted, add them up, and that gives us the Pearson chi-squared test statistic, which is then plotted on the chi-squared distribution. It doesn't show that here, 3.782. So we would take the 3.782, and we go over here, and we'd go find the p-value, 4 degrees of freedom, 3.782, and then the p-value right here is that, which we see in the output, 0.4363. And there it is right here, and there it is right there on the screen. So we need to know one last thing. Since this is a 3x3 table, the degrees of freedom formula is what? So this is a 3x3. The degrees of freedom formula is what? So remember, 3x3, delete one row, delete one column, 2 times 2, and there's 4. Now, if you're wondering why it's a 3x3, but it looks like it has 4, don't count the totals. Remember, there's 3 regions, there's 3 political ideologies according to this, and so we go -1, 2 times 2 is 4. So whenever you do the formula, it's rows -1 times columns -1. So if you just look 3x3, 2 times 2, 2 times 2 is 4 degrees of freedom. And the degrees of freedom control the shape of the chi-squared. So you can see as it gets more degrees of freedom, it becomes more normal, and the center is where the shape is. Or the shape or the degrees of freedom is where the center is. That's got this question here. We'll put the answers in because we pretty much have everything we need. But once again, it's not about solving this question. It's knowing how to solve it. What was the chi-squared again? Chi-squared in the output is like 3.782. I'll make sure we get it right. 3.72. It was 3.72. 3.7. And then this was a neat little number. I think that was right. I'm going to double check it here in a second. I think I got it right. So since the p-value is extremely high, we fail to reject the null, especially at the 0.05 alpha. My p-value of 0.4363 is above the alpha level of 0.05. I fail to reject the null that they're independent. The region is independent of political party. I do not have evidence for the alternative right there. So we fail to reject the null. There is not sufficient evidence that region and political party are not independent. I think right there is not sufficient evidence. Cool. Oops, I didn't click it. think I got through. Yep. And so do remember when you write out your null and your alternative, we wrote these out yesterday. Let me go back to where we wrote them. Here is the interpretations for the test. Here's the interpretation for the interval. My p-value of, state your p-value, is less than greater than my alpha. State your alpha. This means I do not reject or do reject. I have evidence, and here's the confidence interval interpretation. So take screenshots of these or write them down yourselves because these are very important to solving questions. A certain story describing a war. Let's do that one right here. Fun stories. Here we go. So when we do this, you ready, Robert? We got this. Certain story describing a war. Stat 201, chapter 19 quiz. A certain story. There we go. So the first thing you want to do when doing your hacks method, I love the hacks method right here, is you want to write out your what. When doing the hacks method, you want to write out your what. This is the hacks method right here. You want to write out your hypotheses. You want to write out what you're stating to believe to begin. And when we do this right here, it's really easy to write out the null and the alternative for the chi-squared test of independence. What is the one word we put between for the chi-squared test of independence? We don't use notation for this one. So for the chi-squared test of independence, we only do what right here? So for the chi-squared test of independence, we only do what? What do we do? Jesse's got too many points. Jesse's got all the points. So what do we do for the chi-squared test of independence? So this is the way to memorize it. It'd be like, oh, when we do it for the chi-squared test of independence, all we do is write independent between them. The alternative is going to have not right there. So remember, you want to think about what this means. What does it mean for two things to be independent? Well, independent means it wouldn't tell you anything about it. So like where somebody was injured is not going to tell you anything about the lethality of the injury. So there would be no association. Like if you're injured in the pinky versus injured in the neck, it's not going to tell you any sort of difference on the lethality. This is a war story right here, so not a fun topic. So with this right here, the null hypothesis has independent for the chi-squared test of independence. There are other ways of stating it, though. Another way of stating it is the site of injury is not associated with the lethality. The site of injury would tell you nothing about lethality. Those are other ways to state it because that's what independent means. So we do talk about memorizing things, but don't just memorize it. Think about what does independent mean. I'm at the meme tier level. There we go right there. Site of injury and whether or not it was lethal are independent. Site of injury, whether or not it was lethal are not independent, will be the null. Now, this part right here is a longer work to do. Let's just solve this one right here. If you want some really good practice, solve every value in the table. You'll probably be a lot more ready for the test by doing that. So with this right here, what would be the value in the table? Now we're looking for the expecteds. Let's talk a tiny bit about what an expected means. And I think the best way to talk about what is an expected is for us to understand we can calculate these things without even knowing statistics. So think about this. If I tell you, let's look at people who eat cheeseburgers and people who pass the test. So here's a cheeseburger. Did you have a cheeseburger the night before the test? And did you pass the test? So pass the test, we had 300 students, or let's do this easier. 700 students passed the test. 300 students did not pass the test. So now when we look at this right here, we had only 100 students. Make it even easier. Only 100 students had a cheeseburger and 900 students, oh my gosh. Want to reverse this. 900 students passed 100. Okay. So think about this, 12 million, right? So look at this table right here. Oh, that's passed is 500. Half the students passed, half the students did not pass. So of the 900 students who ate a cheeseburger, how many of them would you expect to pass the test? So of the 900 students who ate the cheeseburger, if half the students passed and half the students failed, then how many of the 900 would you expect? Not saying how many did, but how many would you expect to pass the test? So we're asking about the value in here, like for the E, for the expected. So if 900 students had a cheeseburger and half the students passed the test, how many of the 900 would you expect to pass the test? If you can get this, you kind of know what's going on with expected. Now, we're not saying maybe everyone who had a cheeseburger passed the test. So maybe it's the case that, well, it can't be. We could have 500 here. But how many of the 900 would you expect to pass the test? Well, if there's 900 people and half of them, half the people, 450, great job, yep. So 450 is the expected. And the way that works is we divide by the grand total. So we do row total times column total over grand total. Now we might have seen only 380. Now look, there's a big difference. This is the observed. So this is what we observe. And then this is what we expect right here if there is no relationship. So this equation right here, row total times column total over grand total, gets you the expected. And that just tells us what we would expect if the null is true. So very important right there. So let's just do one of ours. How many would you expect right here, Robert? So how many body injuries would you expect to not be fatal? And the answer is going to be doing this equation right here. So you can solve all of them out. How many body injuries would you expect to not be fatal? There is the math. So it's row total. I'll highlight them as I say them. Row total times column total over grand total. And look at how it points in on that cell. So how many body injuries would you expect to not be fatal? That is the equation written out right there. Row total times column total over grand total. And solving all these out is not a bad idea. Just it creates the muscle memory of solving them, and then you remember how to solve them for the test. Like, oh yeah, row total times column total over grand total. 14.4, that sounds about right. So let's see. Now here's the easy way to do it. You ready? We're going to take this table right here, and we're going to go copy to clipboard. So click on that table, copy to clipboard. Let's go and do it. Hit Control-C or Command-C. Now that we've copied it, let's go here to Jump and go to File, New, Data Table. Inside of Jump, go to File, New, Data Table right there. File, New, Data Table. Once you're inside of the File, New, Data Table, you want to go ahead. I like to full screen it, but don't click inside of it. Edit, Paste with column names. Edit, Paste with column names. It has to be with column names. Once you've pasted with the column names, you'll see here a red column, blue, and blue. Red, blue, blue. You can then go to Tables and go to Tables Stack. Under Tables Stack, click the blue columns only until they populate this area right here. You can also drag and drop them, but make sure you have the blue columns right there. Now that you have the blue columns there, go ahead and click OK. Now you'll see right here, this is site of injury. We're double clicking. This is optional, but I like to double click them and change them to something that makes more sense. We add them right there. You can double click and rename them. So just double click, rename. Not required. As long as you have red, red, blue, you've done this correctly. So now that we have red, red, blue, let's go here to Analyze, Fit Y by X. Analyze, Fit Y by X. With Analyze, Fit Y by X, we're going to ask, does the site of the injury explain why there is a certain outcome? But don't forget to put the data into frequency right there. So does the site of injury explain why there is a certain outcome? Just read it like that right there, and then make sure the data is in the frequency. Let's go ahead and click OK, and we basically see the same table we have over here in my Pearson. Confirm that it looks the same way. So you see this table right here, and we see in the jump output the table over here. It's got percentages that we don't want. I'm just going to uncheck these under the red arrow. So we're just going to uncheck these, and now we can see it looks virtually identical with the same numbers. Now remember, we calculated this value over there, so that's where we calculated the mathematics, And Robert said it was 14.4. Let's go ahead and click right here and go to expected. And there it is right there. 14.4. It rounds to it. So I think you can change the decimals if you want. There's a way, but it's a little hard to do. But it's probably going to ask to 2 decimals. So what I'm going to do is I'm going to take a screenshot of this. These are all the expected counts. We already calculated one of them by hand. So that is what we'd have to do. I'm screenshotting it and putting it over here to the side so I can see it while I enter it in. And here we go, 56.60, 14.4. That does round to 2 decimals. 33.48, 8.52, 23.92, 6.08. There we go. Compute the chi-squared statistic. So the chi-squared statistic is the what of all the cell chi-squareds. So to get a cell chi-squared, well, it's the sum of all the cell chi-squareds, but how could we get a cell chi-squared? Now remember, we're not just trying to solve this problem, we're trying to remember the steps to solve it. So go ahead and try to calculate this cell chi-squared right here. And it should be about 1.6 or so, 1.6, 1.7. So take a moment right here. Robert, if you're watching, calculate the cell chi-squared because the count is the observed. So that is the observed right there. So try to calculate the cell chi-squared, which is going to be the observed minus the expected. Then we square that difference. Then we divide by the expected. And this will get us a cell chi-squared. Like how far away are those numbers in a standardized metric? So we get the cell chi-squared right there. So try to run those numbers really quickly. See if you can get the cell chi-squared, which is just a metric of discrepancy for a cell. Discrepancy meaning difference. So how different are those numbers? Well, we square it to turn it positive. We divide by the expected to standardize it, and that'll be how far away are those numbers. And so it should be about 1.6, 1.7. And this is finding a cell chi-squared, just one of them. There's 6 of them total, because each one of these is a cell inside the table. So we'd have to do it for all of them. We'll see that done here in a moment. So the math is going to be observed is 9 minus expected of 14.40 over, and we square that difference. That's about 5-ish. And then we divide by the 14.40, and that is going to equal 1.7. I say 1.7 as a guess. So 9 minus 14.40, square it, divide by, ooh, it's bigger than I thought. It's 2.02. 2.03. I said 1.7 as a guess, and it's close. And then we go over here, and we simply take and add the cell chi-squareds, and there they are right there. And there's that number we just calculated. It also carried more zeros than us, but we got pretty close with the 2.025. So once we get these numbers, we have to take every one of those numbers and add them up to the Pearson chi-squared test statistic. The sum of all these numbers, all these cell chi-squareds, which we just talked about a second ago, every one of these added up that's the big difference down there on the bottom. There it is right there. There is the Pearson chi-squared test statistic. So you don't have to do this by hand, but always know that if you were to take these values right here and sum them up, you would get the Pearson chi-squared test statistic. And there, oops, there it is. Type a whole number. Well, oh, no, degrees of freedom. Oops, chi-squared test statistic. Here we go. 2 decimals. So there it is. How many degrees of freedom does this have? This is a what by what table. So this is a what by what table right now. I'm going to pause for someone to answer right here, but this is a what by what table. What kind of table is that? That is a what by what table. What do you think it is? Be very careful. This is where mistakes happen. So you have to think these are the steps. Step 1, to do the degrees of freedom. That's a what by what table as the very first step. So we have to look right here. There's a certain error people make a lot of times. So to do the what by what table, we say this is a 3 by 2 table. Let me mark that again. 1, 2, 3, 1, 2. So it's a 3 by 2. So since it's 3 by 2, 2 times 1, just drop each one by 1. Because the formula is -1 here, -1, and then multiply these. And that is going to be the degrees of freedom. So I like to just hold up my fingers and be like 3 by 2, 2 times 1. And we can see here in the output, because the output even tells us that the degrees of freedom are 2 right there. So other than we should know how it's calculated, but the output will tell us the answer to confirm. So the degrees of freedom are 2, and the p-value is going to be basically 0. This is because, if we go to the chi-squared applet, so here's the chi-squared applet in the chat, you can go right here and enter in degrees of freedom 2, and then your chi-squared test statistic, and then the area to the right of it is basically 0 because there's nothing to the right of it. Something we wouldn't ask you to do on the test, but also JMP will show you this. And if you look, here's the p-value in JMP. If you hover over it, it will tell you. It's going to tell me eventually. Come on. There it is. -9, 5.4 e to the 7, -9. And what's really great about the applet is if you ask it for enough decimals, it'll basically do it right there, 5.4 e to the -9. So you can get the same numbers from here, but that basically is 0 because you'd have to carry out a lot of decimals, a lot of 0.000000000 to eventually get to it. There's no area to the right of this. So for all intents and purposes, this is basically a p-value of 0. So once again, we have to think about how we interpret this. And do remember, we have our interpretations written out right here, where my p-value of 0 is less than my alpha of 0.05. This means I reject the null, that the two things are independent, site of injury and outcome of injury are independent. I have evidence for my alternative that they are not independent. So I reject the null at the 0.05 level of alpha with a p-value of 0 and conclude that they are not independent. So we should have it all right there. So really good problem, but just remember the steps right here. Don't think about it as solving just this one problem. That's something we keep pointing out, is it's not about this one problem. It's about knowing the steps, knowing what you're doing, knowing how the cell chi-squareds are calculated, knowing how the Pearson chi-squared test statistic are calculated. Really, this problem right here, other than the conditions, condition 1, random, condition 2, less than 10%, condition 3, expected cell counts are all greater than 5, which this passes just barely on this one. Expected cell counts are greater than 5, and condition 4, it's count data. If it had mentioned all 4 conditions, we would have had it right there. So remembering the 4 conditions. And I do want to point to this. Advice for reviewing, we might end with this right here. Oh, we got thunderstorms outside. So, I typed it in wrong. Let's go look at review 3 really quickly, and let's do a little advice for reviewing. Advice for the final. So if you are watching this video right now, if you are watching this, then I highly suggest you go over here to the review 3 page, which is the current pinned message in the chat if you're reading the chat. What you'll see right here are practice exams with keys. So you got the practice exam, you've got the key. I'd go over those. So print off the exam if you can, work through it, see which problems you get stuck on, go over the key, and then practice the problems. Also, there are review videos for all the problems. So if you want, and I try to make them really good where you can go through here and see how we solve them, going over each part, talking about the null and alternative, talking about what everything means. You can see the 3 alternatives right there written out for you. We don't use all 3. It just depends on the researcher's question. Talking about what the standard error is via the formula. There's the formula for the standard error. That's the difference up top right there. So there's the difference divided by the standard error. And if you divide those two, you will get the t ratio. So there's the difference divided by the standard error, and that gives the t ratio. Good stuff right there. But once again, I try to explain every little step with this so that you can see what's going on and where we're getting each parts of these. So I do highly recommend these videos. And following through, our p-value of this is less than 0.01. Reject the null. We have evidence that, yeah, wow, look at this. This is what I did. I did this video, how long ago? I did this video 6 years ago. Oh my gosh. Ay. Almost 6.5 years ago. 6.5 years ago, I made this video. And with it being made 6.5 years ago, the way I interpret the conclusions are basically identical. I do state the null a little bit more often, but my p-value of blank is less than or greater than my alpha of blank. This means I reject or do not reject my null that blank. I have evidence, do not have evidence for blank. So think about how that works. And remember, we're just doing the steps and learning how to write these things out. And I try to break it down. I think that's what I've done more often as I've taught longer, is be like, what are the components of what you need to know and how do we put those together? So you can see right here where we write the statement.
Equals to.
Oops.
Substitute in
I
the
just
greater
blink it
than
on.
the greater.
There's
Behind
those.
it. We see less than for this next part. It's harder to reject.
So that's on power right there. So with this, here's what I suggest doing if you're trying to study for the final. If you're trying to study for the final, go through the practice test, but then also be taking notes. Go to the speedrun videos. Speedrun videos right here, when we compare the means, that's the chapter we were just talking about. Speedruns are just kind of the cliff notes.
Dependent sample.
And you can see here we're talking about side-by-side box plots where we're comparing the difference between two means. And they need to be independent samples, one of the conditions. There's the standard error, talking about that. Independent, there's the degrees of freedom. There's the difference. We're talking about confidence intervals here. The difference, the sample mean 1 minus sample mean 2. The T determines the confidence level. And yeah, going through here, talking about the jump output, very important. All those ads for statistics stuff. But the speedrun videos are going to help you out, but take notes. You should know every one of these topics right here. You should know every one of these topics. Concept review, I think, is really great because I've got examples of each one of the things that you could be doing. Right here, we've got the 4 steps. I do it a little bit differently now. So here's the 4 steps right here. Write out your null alternative hypothesis. Perform the calculation for the t, the z, or the chi-squared, and check conditions. Next, we have here find the p-value and state your conclusion. I decided to call this the hacks methods nowadays. So this is me just talking about the steps. But once again, stating your conclusion right there is going to be the end of it, which we already do anyways. But this didn't really serve for an acronym. We just, I don't know how to say that as an acronym, so I came up with hacks instead. The 2 sample T we just did, and this is an example right here where you will see me write out all the notation. We don't solve that formula. That's the too complicated formula. But you will see me do every bit of notation for every problem right here. Then you will see me do an example problem, and then you will see me solve the example problem using the steps I just described to you, where I solve for the t, I solve for the p-value, and then I state my conclusion at the end. So these are the steps that we've been doing, just slightly different name for them. The t-test, same thing right here for any of the videos. You'll see in the t-test, all the notation is written out for you to begin with. Oh, did it annotate these? Or did I annotate these? No way. I think this is no way. Whoa. This has been bookmarked from Google. Google went... This, I think, was done by AI. Good to see her, Sheena. YouTube figured out the correct bookmarks in this. Because if you notice, it says conditions, equation, p-value, results, conclusion. Whoa. Yeah, I didn't add those. That's generated from Google. That is so crazy. There's me the intro of me telling you it. I think they're noticing the bold in the words. Oh, is this called conditions? Yeah. Must have talked about conditions there. And then this is equation. And then p-value. It recognized that maybe because of the graphic. Results. And then conclusion. That's absolutely insane. It did a decent job bookmarking it. That's the only one I think bookmarked. That's so cool. Well, wish they were all bookmarked like that. I guess I could go in and do it. But these videos right here I think are super duper helpful for understanding the concepts. You get an example of where I walk through, talk about what we use this for. Then you'll see me do the notation of it. Then you'll see me go through here, do our steps for it. Talk about how to solve each portion like we were just doing a second ago with the chi-squared. So I talk about all the mathematics. Then we find the p-value. There's degrees of freedom. Next, we come to our conclusion. We reject or fail to reject. So this is where I enter in the data. Wow, it's going to be done here in a second. Oh, maybe I'm just showing you how to put it into jump. Oh, yeah, there we go. And there's the p-value at the bottom. Oh, really? That video is covering right there. So anyways, with this, the big point is this. It's going to come down to the time you spend reviewing and how you optimize your time. So I would suggest going through here, watching the videos, writing down notes while you're watching them, and thinking about what you're trying to learn. You want to get to the point where you go to the formula sheet and you understand what the formulas are. Like, why would we use the proportion test? Well, the proportion test is when we have a categorical variable and we want to estimate the true proportion. So we'd make a confidence interval. We could do the hypothesis test if we think that each proportion is true, a hypothesized proportion right there. And we want to test it against what we saw to see if we should reject our null, which is maybe I believe 40% of UT students own a dog, which would be P naught, but I see 50% own a dog. So how far is that distance away in standardized units? Standard deviations right there. All of these right here have an understanding of why we use them and when, because that comes into play with tools and techniques. So if you have any questions, please let me know. We'll do some review sessions. We have the Kahoot coming up. But I think that's got it for now. But that's my advice for reviewing. Just put it into parts. Go through the review sheet and think about what you're trying to learn. And yeah, so the review sheet is right here. There's tools and techniques. Here's the topics. Go through and we have a video going over each one of these. Until then, bye for now, everyone. Bye.